The basics have now been covered, and so on to the traditional measurement methods. This is a rather short section, but it is nonetheless important because the Dirana method is often compared to the traditional approaches. For this reason, it is important for you to know how reliable the old approaches are. One of these methods is called Karl Fischer titration, named after a German chemist. Karl Fischer lived at the beginning of the last century. In 1935, he invented a chemical method for water analysis, using water reaction in a reaction cell. Karl Fischer's titration method can measure very precisely how many water molecules react inside the cell. This method is often used as a standard or scale for other water determination methods. However, it is subject to a lot of influences. For example, the sample has to be taken from the transformer and then transported to a laboratory. Because the air outside is usually wet, the sample arrives at the laboratory with a higher moisture content than it originally had. Sample preparation also varies in different laboratories. There are different titration systems on the market and different manufacturers of titration systems using varying techniques. Temperature also influences the result, but it is not intended to go into detail on this subject, but simply to highlight that even this Karl Fischer titration standard or scale is influenced by errors. The following quick test illustrates graphically how reliable or even unreliable the Karl Fischer titration method is. What has been done? 3 samples of oil-immersed paper were sent to 7 laboratories. The bar graph compares the moisture content in the 3 samples as obtained by the laboratories. In an ideal case, all 7 laboratories would produce results showing the same moisture content. But will they? First, looking at sample A on the left-hand side. Here results were from 1 to 2%. For a further wet sample, the results ranged between 2.2 to 3.6%. This shows that even under laboratory conditions, the Karl Fischer titration method gives different results if several different laboratories are used. There was also a systematic deviation between the laboratories. One laboratory always measures 18% more than the average, and the other laboratory 22% less than the average. Now consider the case that someone measures water content using the Omicron Dirana system. The paper samples are sent to a laboratory. The laboratory confirms the water content was 3.2%, but Dirana indicates 2.5%. How can this difference be explained? It has clearly to be understood that the titration method itself cannot provide such a high level of accuracy, and that this must be taken into account in any final analysis using other methods. Differences will also appear when comparing different dielectric response methods to each other. For example, one customer may utilize the Dirana to test his transformer in the first instance, then later may measure the water content using a competitor's product. Both instruments will give different value for water content. In this case, once again, the explanation must be that there are differences even under laboratory conditions, and because of this, there will be differences for dielectric response methods as well. The next diagram compares the results of moisture in oil, again done as a round-robin test. 2 samples of new oil and 1 of aged oil were sent to the same 7 laboratories. What did the laboratories find in this case? Here the scattering was even worse. For the dry sample, the results vary between 3 ppm and 12 ppm. For the wet sample, between 35 and 340 ppm. Now consider applying these inaccurate results to an equilibrium diagram. It will also show scattered or poor results. For sample B, with a moisture content from 6 ppm to 20 ppm at a temperature of 25 degrees Celsius, the equilibrium diagram gives us 2.5% to more than 5% for moisture content in paper. This is the old approach, which has been used for decades and is used even now by many transformer operators. So, to underline it once again, it gives a poor accuracy, usually such that the indicated moisture concentration is too high. There are even more influences on the equilibrium approach in terms of aging. Aging changes the moisture absorption capacity of oil, and so the equilibrium curves shift, and so, depending on the state of aging, we will have different equilibrium curves. There are also some new methods to measure moisture in oil, so-called capacitive probes. Capacitive probes measure the change of capacitance caused by water molecules. Water molecules migrate into the dielectric of a capacitor. They change the capacitance, and by this change, moisture can be measured. These probes will give only moisture saturation. They cannot provide moisture content because they depend on moisture equilibrium. For historic reasons, the transformer operators wanted to use ppm, that is, moisture content, to indicate moisture in oil. Thus, the manufacturers of these capacitive probes delivered equations to calculate ppm for moisture saturation. Nevertheless, this is valid only for the specific oil to which the probe is calibrated. Different oils will have different water solubility. So the probe should be calibrated to each of the individual oils in order to get the right moisture content. If one uses such a capacitive probe and then applies it to an equilibrium diagram with a new shape, much more reliable moisture determination results can be achieved. A new shape means that the diagram shows moisture saturation instead of moisture content on the x-axis. If a customer now compares the Dirana reading to such a new equilibrium diagram, then the comparison makes sense. Some practical cases will be shown later which show that there is a good fit between Dirana results and such new shapes of equilibrium diagrams. Now we have a summary of Part 2, the titration method according to Karl Fischer, which delivers moisture content in oil or in paper. In particular, this section shows how results can be affected by a lot of external factors, and why it is difficult to compare results from different laboratories. The use of capacitive probes as an alternative approach. Using capacitive probes to measure water relative to saturation, and the resultant improved reliability and comparability. Equilibrium diagrams, and why they are very inaccurate for the conventional representation using moisture content in oil in ppm, but identifying why they are reliable if they use water saturation in oil.